Right, so here's a question. Is a polyhedron always guaranteed to be convex? Again, our definition of polyhedron. So, the first step is a half space convex? Why? You can see visually that it is convex, but that's not enough for us. You say something, you should be able to prove this rigorously. Just go by the definition. Take 2 points that belong to the half space. See if it's still and some convex combination of those points. Does that still belong to the half space or not? So let's consider the half space. Let's call it H, which is the set of all x in Rn such that A transpose x is, say, greater than or equal to B. And pick 2 points, say x1, x2. Okay, so which means that A transpose x1 is greater than or equal to B and A transpose x2 is greater than or equal to B. That is what we know for sure. Right? So is it true that alpha x1 plus 1 minus alpha x2, if for this to belong to the half space, we want A transpose this should be greater than or equal to B, right? So this is just alpha times A transpose x1 plus 1 minus alpha times A transpose x2, but x1 and x2 both belong to the half space, so A transpose x1 is greater than or equal to B, A transpose x2 is greater than or equal to B, so this is alpha B plus 1 minus alpha B, which is just B. So alpha x1 plus 1 minus alpha x2, this also belongs to the half space H. The half space, we know that a half space is convex. Now, what about intersection of, after all, what is a polyhedron? It's an intersection of finitely many half spaces, correct? So let's try to make a more general statement. So I give you 2 convex sets, say C1 and C2. Is the intersection of those two also guaranteed to be convex? If C1 and C2 are convex, then C1 intersection C2 is also guaranteed to be convex. Again, how do you prove this? You take any 2 points x1, x2 that belong to both C1 and that belong to C1 intersection C2, that should belong to C1 and C2, right? If x1 and x2 are elements of C1 intersection C2, then x1, x2 belongs to C1 and x1, x2 belongs to C2. So if you take any alpha between 0 and 1, this point belongs to C1 because C1 is convex. This belongs to C2 because C2 is convex. Right? Because we assume that both C1 and C2 are convex. So alpha x1 plus 1 minus alpha x2 belongs to C1 intersection C2 for all alpha between 0 and 1. So the intersection of convex sets is convex. And in fact, it holds true not just for intersection of finitely many convex sets, but also an intersection of infinitely many convex sets, because the same argument just goes through. Okay. So a half space is convex, intersections of convex sets is convex. So any polyhedron is guaranteed to be convex. Okay. But again, you have to be a little careful when thinking about polyhedra. I mean, of course, the polyhedron, as we defined, it's an intersection of finitely many half spaces, right? And when you try to think about polyhedra in, let's say, in 2 dimensions, first thing that you think about is polygons, right? And not all polygons are guaranteed to be convex, correct? So, for example, I could just draw a polygon that looked something like this, right? Is this a convex set? This region, it's not convex, correct? So then is there an ambiguity? So is there a problem here in terms of the definition? Well, not really, because you have to think, can this polygon be written as an intersection of half spaces? Yes. So if you think about a convex polygon, let's consider something like this, some sort of a weird pentagon. I could write this as an intersection of the half spaces, which are essentially defined by the sides of this particular polygon, right? So this is one, take this to be another, this is a third, a fourth, and a fifth, right? So this convex polygon could in fact be written as an intersection of half spaces. But on the other hand, can you do the same with this weird non-convex polygon that I have drawn here? No, because if I look at, let's say I draw a half space which is defined by this edge and another half space that is defined by this edge, what is the intersection of the two half spaces? Yeah, it will only be this bottom part, right? It would be this region over. It would basically be this region over here, right? So polyhedra doesn't necessarily equate in a one-to-one fashion with polygons. Every convex polygon is a polyhedron. A non-convex polygon is not a polyhedron by our definition. Okay, so there's a subtle distinction between polyhedron, and so you can construct something like a polyhedron or an extension of a polygon in higher dimensions, but which is not necessarily convex. Right. So that's something to keep in mind. In fact, as we'll see eventually, as we saw here, a polyhedron is an intersection of finitely many half spaces, right, which is convex. What is perhaps a little more surprising is that any closed and convex set can be written as an intersection of potentially infinitely many half spaces. Right? It's a little deep, but if you think about it, let's say I take this, let's take the circular region. Now I can construct a tangent at every point on the circumference of this particular circle, and consider the half space that includes the circle, right, on the side of the circle. If I take the intersection of all of these half spaces, there are uncountably infinitely many such half spaces. If I take the intersection of all of these, what do I get? The circle itself. Right. So it's an intuitive way of thinking about it, but still it's a little surprising that just half spaces are enough to generate any arbitrary convex set. Closeness is required. Even in this case, can you generate the circle without the circumference using an intersection of these? No. So also you can see why closed is required, because a half space is always a closed set by definition, because we've defined the half space as set of all x such that A transpose x is greater than or equal to B, and an intersection of any number of closed sets is guaranteed to be closed. So if you take another way of saying what I said earlier, was that if you have any convex set, then the closure of that convex set can be represented as an intersection of half spaces. Any questions from this or what we discussed in the previous class?
A slightly general question, but we were talking about how an infinite intersection also informed polyhedron.
No, not polyhedron. So polyhedron is always an intersection of finitely many half spaces.
Yeah. So infinite intersection with convex is convex.
Yeah.
So, but in general,
yeah,
when does extending induction to infinity will work?
It's a little hard to say. So, I mean, I can't give a general statement, but I can give a non-example, which is sure. So for instance, the union of countably infinitely many closed sets is not guaranteed to be closed, right? So a union of so suppose that I have closed sets A1, A2, and so on, countably many. Then union I equal to 1 to infinity AI need not be closed. In fact, this was supposed to be the question in your first exam, but the union was, there was a typo and the union was replaced by an intersection. But okay, can you give me an example? Yeah. A by NB. Okay. So basically you take this A fine, whatever, A, B plus, does it matter? Okay, B minus. So if I define AI to be equal to this, where for some A less than B, then each AI is closed. But what is the intersection of all of the AIs? A comma right, it's this, so it's half open. I'm sorry, what did I write? Union. So union of these gives me closed A comma B. Sorry, closed A, open B. Right. So even, for example, if you take AI to be the set 1 by n or 1 by I, since my index is right, this is also an open set. Sorry, this is not an open set. It's not a the intersection of the union of the AIs is not closed because it doesn't include the limit point 0. Yeah. Which one? So okay. So yeah, this above.
What the, can you repeat this that you said again? So the closure of what is definitely many half spaces.
So basically,
The
if
subspace, the subspace.
if C is convex, right, then closure of C can be represented as an intersection of half spaces. How many? Depends. If it's a polyhedron, then finitely many, but in general, it could be infinitely many. Okay. Any other questions? Yeah, again, it doesn't perhaps answer your question as to when you can extend something, when something about finite collections of finitely many sets can be extended to properties of that hold true for finite collections of sets extend to infinitely many sets, but you have to be careful. Right? The main point to note is that if you have finitely many sets, then the union will also be a closed set. Any other questions?
How do you close the infinitely many
Which one?
intersections?
It basically follows from the same argument. I'm guessing that your question is the intersection of infinitely many convex sets. The same thing, right? If you have x1 and x2, that belongs to the intersection of all of the all of the sets, then x1 and x2 belongs to each set Ci, and therefore alpha x1 plus 1 minus alpha x2 belongs to each Ci, and therefore it should belong to the intersection of all of the Ci's. It doesn't matter what the index set is. Okay, so far we looked at convex or convex sets, affine sets, conic sets, and their properties. Today we'll switch from sets to functions. All right. So what? Yeah. Yes.
Here over AI is a point. An is like a 2 cross 1 point.
Which one? So in this case, it's an interval, right? So in this case, in this example, it's an interval. In this case, it's a singleton set. Okay, yeah. This means the interval from a to b minus 1 by n. Okay, so what is a convex function? A convex function, so any function defined over some domain, where we'll assume that the domain is a convex set. So f takes every element of this convex set A and outputs some real number. So this is convex if basically f of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha f of x1 plus 1 minus alpha f of x2. This holds true for all x1, x2 in the domain and alpha in 0, 1. A related definition is the function is said to be strictly convex if f of alpha x1. So if you take note of this, what happens when I set alpha equal to 0? What is alpha x1 plus 1 minus alpha x2? It's just x2. It's guaranteed to be equal. The left hand side is guaranteed to be equal to the right hand side. Similarly, if I set alpha equal to 1, again have equality, right? So if this equality does not hold at any point alpha, which is strictly between 0 and 1, then it is said to be strictly convex. Holds for all x1, x2 in the domain and alpha in the open interval from 0 to 1. So again, what is the geometric interpretation of this particular definition? You take any function, right? It could be perhaps if it's convex, then what does the definition say? You take any 2 points, let's say x1 and x2. This particular point corresponds to f of x1, right? And the value of f at this particular point is f of x2. Right? What can you say about alpha x1 plus 1 minus alpha x2? Where will that lie? For alpha between alpha x1 plus 1 minus alpha x2. So it's some point that lies in between x1 and x2, right? For alpha being between 0 and 1. So let's say this is my x, which is alpha x1 plus 1 minus alpha x2. Correspondingly, this would be f of alpha x1 plus 1 minus alpha x2. What can you say about alpha f of x1 plus 1 minus alpha f of x2 as you vary alpha from 0 to 1? Yeah? Goes from x1 to x2 where? So what can you say about the set of points alpha x1 plus 1 minus alpha x2 comma alpha f of x1 plus 1 minus alpha f of x2. So this is a pair of points for every alpha, and you vary alpha from 0 to 1. What kind of a function does this define? Correct. So this essentially corresponds to the line segment that joins these 2 points. Correct? So effectively what the definition says is that the function is convex if the following holds. You take any 2 points on the curve that defines the function, then the line segment joining any 2 points on the curve is a strict upper bound for the function of the curve itself. That is, this line segment should always be above the curve that defines the function. Yeah.
Suppose I take x1 at the minimum.
You take x1 at the minimum. That's okay. Fine.
Then
Not a problem. So let's take something like this. You want this to be your x1. I'll take this to be my x2. What happens to the straight line that joins x1 and x2? It would just be this. Right? This line segment is guaranteed to be above the function itself.
but x1 plus 1 is somewhere between x1 and x2.
Correct.
And that f of alpha x1 plus f of alpha x2 like will be some the line will be below that.
No, right?
Can you draw it?
So this is your x1. So where do you want x to be? So alpha x1 plus 1 minus alpha x2 is going to lie between x1 and x2. Right? It doesn't matter. You want to keep it very close to x1, that's still fine. This would be your x.
Now, can you draw f of alpha x1 plus?
This is the value of,
f of.
correct. So that's the function value at this point, right?
But there is some part of the line which is less than.
There is no point. Which are you talking about, the line segment or the function itself?
The line segment.
The line segment will never be below this, right?
There is
Which?
like some part, like suppose that x, the second x which you draw,
This.
the right side x.
Yeah.
Now can you draw a horizontal? Like yes.
This.
Horizontal.
Okay, so this is your.
There is some part of the line below.
There is some part of the line,
Yes.
correct. But then if you look at alpha f of x1 plus 1 minus alpha corresponding to the alpha that defines this particular x,
Yes.
that is guaranteed to be somewhere above this. That is by definition.
Is this function strictly convex?
This function is strictly convex.
But equal to x1 equal to x.
That is why I chose x1 equal to x2. Okay, then maybe I should be a little more careful. I should just say x1 not equal to. So geometrically convexity doesn't. So by convexity, if the function is convex, then all you can say is that this line segment that joins 2 points on the curve lies strictly above the curve. So there could be some point on this curve whose function value is larger than some point on this line segment. That is okay. But if you look at it sort of vertically, this line segment is guaranteed to be above this curve between these 2 points x1 and x2. Right? Does that make sense? Right? But on the other hand, if you take a function that you think is not convex, perhaps the function looks something like this, right? Then it will be possible, if the function is not convex, it will be possible to take 2 points such that the line segment intersects the curve or it goes below the curve. Right? There is a notion of strongly convex. We'll get to that a little later, but basically strongly convex, yeah, let's wait for it a little bit. But that's a different notion than strict convexity. No, it doesn't necessarily. If a function is convex, it doesn't necessarily have to have a unique minimum. Why? Let's take a simple example. Let's take a function that looks something like this. Yep, let's take this function. What is the minimum? Any point on this horizontal line, right? Is this function convex? It is convex. In fact, if you want something that you want to think about more analytically, you can say f of x is, let us say, x for x minus x for x less than 0, 0 for x between 0 and 1, and maybe x minus 1 for x greater than 1. Okay, so this will basically correspond to the same, to a function that looks like this. In this case, the minimum value of f of x is 0, and it's achieved at every point between 0 and 1. So a convex, and this you can very easily prove that this is a convex function.
Yeah. You say that there should be a local maxima apart from the global maximum for it to come.
True. Yeah, we'll see that later. That's precisely the reason why we look at convex functions. It is that every local minimum is guaranteed to be a global minimum, and there are no other stationary points except local minimum.
What about strictly convex functions? Will they have a unique minimum?
Strictly convex functions will have a unique minimum. That is something that is guaranteed. Okay, so you have to be a little careful over here. When I say it will have a unique minimum and it will have a minimum, it could be that the minimum is minus infinity. It's possible to come up with, or it's possible that the minimum is not achieved. For example, if you take e to the power minus x, for x defined, just e to the power minus x. What is the minimum of e to the power minus x? 0. Is it achieved? What is the minimum of e to the power minus x? There is no. The infimum of e to the power minus x is 0. Right. So really, the correct statement to make is that if there is a stationary point, then that stationary point will be a local minimum, and every local minimum is guaranteed to be a global minimum.
So how do you define stationary point?
Okay, good point. A stationary point is one for which the derivative is 0. The first derivative is 0. We'll get to all of that. I'm sort of jumping things a bit. Okay. Now, just as we define convex functions, we can also define concave functions. So there's a notion of a convex set. There's no notion of a concave set. So a set is either convex or not convex. But we can define concave functions f. Now again, this is defined on a convex set A. The domain has to be convex, because ultimately this has to make sense. I want alpha x1 plus 1 minus alpha x2 to be in the domain for every x1, x2 and alpha. So if the set is not convex, this may not even be defined, the left hand side. Correct? So a fundamental requirement is the domain of f should be convex. Okay? Again, what about it? You can't define.
Can you find all the
A piecewise convex functions could have multiple local minima. Not necessarily, you may not be able to find it efficiently. Okay, so a function f is concave if minus f is convex. It's a rather straightforward definition. So for example, e to the power, so e to the power minus x is what? Is it convex, concave? E to the power minus x or e to the power x, doesn't matter which one you take. Both are convex. What about log x? Log x is concave minus log x is convex. Right? How do you prove it? Of course, one way to do it is you follow the definition that we have used. Right? You have to prove for every 2 points x1 and x2 that this holds. In fact, all the 3 examples, so e to the power x, e to the power minus x are both strictly convex, and log x is strictly concave. Yeah. Very good point. Yes, if a function is not continuous, then it cannot be convex or concave. But just I'll come to that in a minute.
Certainly, this piecewise convexity will take care of this.
Again, for what?
You were saying piecewise convexity.
Okay.
So I'll have a convex from say 0 to 1.
Okay.
And then again convex from 1 to 2.
Okay, but again, how does it help is the question. Yeah, you can define it, that's true, but it doesn't make life easier, it just makes our life harder. Right? So a point that I'd like to make here is that now I've defined a function f from some domain to R. So if the function is defined only on some say subset of Rn, right? So if the domain so if this is a strict subset of say Rn, then it is possible to define another function and f is convex. Then I can extend this to all of Rn in the following manner while still preserving convexity. So I can define say f tilde of x, which is equal to f of x for x in A, and for every point that is not in A, I'll just say that it's equal to infinity. Right? It's not a strict function. It's not a function from say the Rn to R, but rather I'm allowing the function value to be infinite. This takes care of some sort of minor technicalities that we may encounter, but sometimes it's useful to think of this extended value extension.
Start off at a point that is not.
Okay, does it in what sense? So I'm not talking about algorithms or anything of that sort. Okay, so just the analysis becomes easier sometimes when we if you think of the extended value extension. Right? It doesn't help us algorithmically in any way. So it's an exercise, prove that this is convex. And it's not very hard to do it. You just take any 2 points x1, x2. If both x1 and x2 both lie in A, then you know that the definition of the requirement is satisfied. F of alpha x1 plus 1 minus alpha x2 is guaranteed to be less than or equal to alpha f of x1 plus 1 minus alpha f of x2. But then if you take either x1 or x2 not in the domain, then alpha f of x1 plus 1 minus alpha f of x2 will be infinite, because either f of x1 or f of x2 will be infinite, and it doesn't matter what f of alpha x1 plus 1 minus alpha x2 is, because the right hand side is infinite anyway.
Didn't it just say that this continuous function
uh, this. Okay, so again you have to be a little careful. So in this case, right, this function is not continuous, but again it's not a valid function, so to speak, because I've allowed f tilde to take infinite values, right? Assuming it's a proper function where f takes only real values. So if f is discontinuous, then f cannot be convex or concave.
We also extend it in a continuous manner.
In general, no. It's okay. I can't think of anything at this particular point, but okay. So I'll maybe take that back. It may be possible to extend it, but there's no generic extension, right? So in this case, I know exactly how to define f at points outside A, right? How you define f at points outside A would potentially depend on the value of f itself. So there would be a continuous extension, but that would depend on the function itself.
Soup of f over a may be a better choice, right? It could be potentially finite.
In which
Instead of
case,
infinity,
correct.
use the maximum of
Okay.
of f over this domain.
Okay. Yeah.
I map everything that doesn't belong to A to that. That would also be convex, right?
No, that is not guaranteed to hold. So, for example, let's think about it visually itself. Suppose that I take some function that looks like this, right? And it's defined only on this particular interval. What you're saying is that outside the domain, I just set it to be max of f, correct? So what would the function look like? It would look like this, correct? Is this convex? No, because if I take, let's say, these 2 points, I draw the line segment joining these two, it lies below the function. So it's necessary. So if you want such a generic extension, then you must have f to take infinite values outside the domain. That's the only way you can guarantee convexity.
But then, as long as any point is outside the interval, there will definitely be a line possible.
How?
Or suppose I take some random point outside, let's take x square minus 10 to 10.
Okay.
Then that will be basically the same thing, and after that, let's take it goes like infinity.
Exactly. Yeah.
Yes. Then, even
Again, that's the
there
problem with infinities, right? You can't visualize it. That's the main point. So it's a technicality, right? It's sort of a trick that you play
like
with infinities.
any by like take it as big as you want or take it as small as you want. There will definitely be a line that is below the comma.
Why?
Because for every
So-
point,
so what is the
there
value-
always exists another y minus.
So let's take the line segment, so to speak, right? What would be the value of the line segment? So the straight line. What is the value of the straight line at any point outside the domain? It's infinite, right?
Can I say it for minus infinity also?
Which one?
Instead of plus infinity, there is minus.
Definitely not.
Huh?
Definitely not. No. Again, just use a definition of convexity, right?
At the boundary of the setting,
Yeah.
you find the slope and have a gradient that is more than.
So again, it could be possible. I'm not saying that you cannot, for a given function, there would be a continuous extension, but that potentially depends on a lot of factors on x itself, on f itself, right? So there's no generic extension, right? This particular generic extension will be useful at one or two other points later on. Okay, that's why we're just using this. In fact, in many cases, we will use, we'll just assume that we'll typically look at functions which are defined all over Rn. But then sometimes it's helpful to use these extended value extensions, particularly for let's say constrained optimization problems. And there's a natural way or a natural reason of considering the extended value extension. Suppose that A is the set of constraints. Now it could be that F is defined over all of Rn and F is convex over all of Rn. Okay. If I look at suppose that A is my set of constraints. Okay. And I look at F tilde. What is the infimum of F tilde over all X? Okay. So the infimum of F tilde of X over all X in Rn, what is this equal to? This is equal to the infimum of F of X, but X taken only from A, right? So in a sense, I can sort of transform a constrained minimization problem into an unconstrained minimization problem. Eventually, it doesn't help algorithmically, although there are some algorithmic techniques that kind of make use of this point. But the point is that the left hand side is an unconstrained optimization problem, or maybe a weird looking function, but the right hand side is a constrained optimization problem.
Can you tell us a bit more about the stationary points, the minima?
We'll get to that. We'll do it step by step. But right now, we've not even gotten to the point of optimization yet. Right? We just want to understand, as we'll see, there are many different useful properties of convex functions. Even different geometric ways of looking at convex functions itself. Right? Okay. So the first point is, if for now I leave it as a homework to sort of formally prove that if F is discontinuous, then F is not convex or concave. And intuitively, you can think of why that is true. So, for example, you take a point just to the left of the discontinuity and a point just to the right of the discontinuity, and the line segment that joins these 2 points, you'll see that it will partly lie above the function value and partly below the function. All right, again, that's just geometric intuition, but you can prove this formula. Very good question. Can a function be both convex and concave? Yeah, so any straight line is both convex and concave. Is there any other function which is both convex and concave? Yeah. So we're looking at functions from, okay, I agree. So if you're looking at f from R2 to R, then it's always a plane. But is there any other function from R2 to R other than a plane which is both convex and concave? Well, in if f is from R2 to R, then it can't be a line, it has to be a plane, the function, because it has to be a surface, right? If you look at functions on R2, every function essentially defines the surface, a surface. So if we just focus on R to R for concreteness. Correct. So is any function which is not a straight line, can it be both convex and concave? What do you mean, circle? Yes.
From R to R should be some planes.
Forget, let's just focus on R to R. I mean, if you have it from R to R, then the same thing extends from R2 to R, R3. Okay, is it true that it has to be a line if it is both convex and concave?
You could prove it with, because one is the greater than equal to one is the lesser than.
Yeah.
What is our has to be a line.
Convex and concave. Then f of alpha x1 plus 1 minus alpha x2 versus alpha f of x1 plus 1 minus alpha f of x2. This has to be less than or equal to this for if it is convex, and greater than or equal to this if it is concave. So if it is both convex and concave, then this should be equal to this, which essentially corresponds to a straight line. What do you mean point? Again, we are looking at functions, right? The function has to be defined over all of R in this case. We're assuming that f is, in general, it could be from Rn to R. But let's assume that it is f from R to R. Right? I mean, geometrically, think about R2, a function is convex if it is kind of like a bowl, it's bowl shaped, and it's concave if it is like an inverted bowl. And the only way it can be both convex and concave is essentially if it is flat. Right? Any other questions?
Continuous function
Okay, so I guess the question is, is there an example of a continuous function which is neither convex nor concave, right? Let's take f of x equal to x cube, right? What does that look like? You want me to not yeah. So, right, let's say from -1 to 1. Looks like something like this, right? So this is neither convex nor concave. There's a certain region where this is convex, there's a certain region where this is concave, But if you take the domain to be, let's say, from minus infinity to plus infinity, then this is neither convex nor concave. What do you mean by circle? Because it has to be a function, right? A circle would certainly define a set, right? If you look at the circle, the region enclosed by the circle, then that's a convex set. Any other questions? Yes? Question? Okay. So that's one sort of characterization of convex sets, of convex functions. This is in terms of the line segment joining any 2 points on the function, right, on the curve that defines the function. There's also another very helpful equivalent notion of convexity, and that is in terms of the tangent, right? The nice feature about convex functions is that if you draw the tangent at any point on a convex function, the tangent always lies below the function, right? And that's called a first order condition of convexity. So right now, so throughout we'll whatever I used the definition of convexity earlier, that's what we'll stick to. That's the definition of convexity. But there are equivalent conditions of convexity. So if f is convex, and let's say that the gradient exists, or let me say, and suppose that the gradient exists over all of A, then f is convex if and only if the following holds: f of x is greater than or equal to f of x naught plus. So if you recall from our earlier discussions, somewhere towards when we discussed multivariate calculus, if you the tangent plane that passes through the point x naught comma f of x naught was equal to f of x naught plus gradient of f at x naught transpose times x minus x naught, right? So the right hand side corresponds to the tangent plane or tangent hyperplane passing through x naught comma f of x naught. So if a function is differentiable, then it is convex if and only if the tangent plane at every single point is always a lower bound on the function value itself. Okay, so if you think about, so this is my f of x, I take some particular point x naught, so this is my x naught, this is x naught, this is f of x naught. The slope of this tangent plane is basically the derivative, that is gradient of f of x naught. So this is the tangent plane, y equals f of x naught plus df by dx evaluated at x equal to x naught times x minus x naught. Whereas this particular function, this corresponds to y is equal to f of x. So you take any point x, be it be some x which is less than x naught. In this case, this is f of x naught, and this is the value of f of x naught plus gradient f times x minus x naught. Right? So the tangent basically lies below the curve for every tangent to the curve. Questions regarding this particular statement? Okay, let's prove that this is the case. So we want to prove both sides, right? That if f is convex, then this holds for all x naught, x, right? So, and we also want to prove that if this holds for all x naught, then f is convex. Let's start with the slightly easier way. Let's assume that this is true. Okay. So suppose that f of x is greater than or equal to f of x naught plus gradient f of x naught times x minus x naught for all x naught. Again, when I say for all x naught, it's within the domain of f. Right? Okay, so suppose that this is true, I want to show that f is convex. So let's consider 2 points. So let's consider x1 to any 2 points, x1 and x2, that belongs to the domain of f, and some alpha between 0 and 1. Okay, I'll define x to be equal to alpha x1 plus 1 minus alpha x2. Okay, so I'll use this particular property with x equal to this particular x, but separately with x naught equal to x1 and x naught equal to x2. That will give me 2 conditions. So f of x is greater than or equal to f of okay, sorry, I should do the other way around. I'm going to take x equal to x1 and x equal to x2 and x naught equal to this particular x. So f of x1 is greater than or equal to f of x plus gradient of f evaluated at x times x1 minus x, and f of x2 is greater than or equal to f of x plus gradient of f evaluated at x times x2 minus x, where I've just used this property twice on the pair of points x1x and x2x. Let me call this inequality 1, this inequality 2. So let's just take alpha times inequality 1 plus 1 minus alpha times inequality 2. What do I get on the left hand side? It's just alpha times f of x1 plus 1 minus alpha f of x2 greater than or equal to, what is alpha times this plus 1 minus alpha times this? It is just f of x itself. And then I have alpha times, so let me perhaps split this. So alpha gradient f of x times x1 minus x plus 1 minus alpha gradient f of x times x2 minus x. Right? So this is f of x plus, I can take the alpha inside, right? So I basically get, and I have f of gradient f of x common in both, so I can just take it out. So this is gradient f of x transpose times alpha x1 minus alpha x plus 1 minus alpha x2 minus 1 minus alpha x, right? Which is nothing but f of x plus gradient of f transpose. Let me combine these two. What is alpha x1 plus 1 minus alpha x2? It is x by definition, right? So this is just x. I just combined these two to give this particular x. And what is alpha x plus 1 minus alpha x? X again, so this is x minus x. These two cancel. So on the right hand side, I'm just left with f of x, which is nothing but f of alpha x1 plus 1 minus alpha x2. Right? So if the tangent is always below the curve and the function is differentiable, then the function is convex. Okay? Let's try to prove the other way around. Let's assume that f is convex, of course, and the gradient also exists. So I have f of x I know that f of, so let's take have 1 minus alpha, let's say x2 plus alpha x1. Just write this in a slightly convenient form. Let's look at 1 minus alpha x1 plus alpha times x2, which is the convex combination of x1 and x2. I can write this as x1 plus alpha times x2 minus x1. Okay, I'll just rearrange the term. So this is x1 minus alpha x1 plus alpha x2. I just group together those two terms, nothing more. So f of x1 plus alpha times x2 minus x1, which is nothing but f of 1 minus alpha x1 plus alpha x2. By definition of convexity, this is less than or equal to 1 minus alpha f of x1 plus alpha times f of x2. Right? I'll just use the definition of convexity here. this is again just by rearranging, this is f of x1 plus alpha times f of x2 minus f of x1. Right? Just this, nothing more than using the definition of convexity and playing around with the terms. Okay. So now let's look at this particular quantity over here. Let's assume that alpha is something that is very, very small, close to 0. If you recall, we know that f is differentiable at x1. So I can expand f around x1. Recall that the definition of the derivative allowed us to write f in terms of sort of the first order Taylor series approximation. So f of x1 plus alpha times x2 minus x1, this is equal to f of x1 plus gradient f of x1 times alpha times x2 minus x1 mu transpose plus some term that decays faster to 0 than alpha. Where basically little o of alpha is some term such that little o of alpha by alpha tends to 0 as alpha tends to 0. Right? The main point is that it decays faster than alpha. Okay, so let's call this equation 4. So basically, if I use equation 4 in equation 3, the left hand sides of both are the same, correct? So f of x1, from 4 I have f of x1 plus gradient f at x1 transpose times alpha times x2 minus x1 plus little o of alpha is less than or equal to f of x1 plus alpha times f of x2 minus f of x1. These two quantities cancel each other out, and I can take this alpha outside, right? Similarly, I have an alpha over here, so I can divide both sides by alpha. So I get that the gradient of f at x1 transpose x2 minus x1 plus something that decays faster than alpha is less than, divided by alpha is less than or equal to f of x2 minus f of x1, or f of x2 is greater than or equal to f of x1 plus gradient f at x1 transpose x2 minus x1 plus this particular quantity. Now if I let alpha to tend to 0, then this particular quantity tends to 0, nothing else depends on alpha. And alpha was anyway an arbitrary parameter that I introduced, right? The only requirement was that alpha is non-negative, whatever alpha is between 0 and 1. F of x1 plus gradient f of at x1 transpose x2 minus x1. Right, so this shows that if f is convex, then the tangent always lies below the function. Okay. So this is an alternative characterization of convexity. But of course, all of this holds only if f is also differentiable. You need an additional condition. But as we'll see maybe in the next class, that even if f is not differentiable, you can use something else in terms of instead of the tangent. Right? Any questions? Okay, so let's stop here.